Hi, everyone. Thanks for being here. I am Sai Nudurupati. I'm a PhD student in the Department of Civil and Environmental Engineering here. My colleague Amanda and I are going to talk about Landlab Modeling Framework. Some of you guys have attended the cyber seminar. I hope you got a little bit of an idea there, but I'm going to go through the slides so that it will be serving as a refresher. First of all, I would like to thank the Landlab team. Those are all the authors of this PowerPoint. It's a highly collaborative open source research. First of all, what's Landlab? Landlab is an Earth surface dynamics modeling framework. It's not a model, or it's not just a model, it's a modeling framework. So we want to help you create models. Maybe new ones, or just use available resources and create a model really quickly with whatever is given or is available in the Landlab framework. So you can create 2D numerical models right now, but nothing would stop you to create 3D models in the Landlab framework. Like I told you, it's an open source resource, or it's an open source library. It's available through Git. And it's written in Python language, so it's easier to couple with external models that are probably written in any other languages. We have a documentation page, which we think is pretty good. If you don't think so, you please reach us, and we can fix things. The web page is landlab.github.io. Let's look at what Landlab provides in detail. It provides robust reusable components, which represents Earth surface process in the framework. A 2D gridding engine for structured and unstructured grids. Data structures that allow you to store data on the grids or manage your data in the framework. And tools for input and output of the data to and from the environment. And we also have utilities that help visualizing your data on the Landlab grids and also the data structures. So what are components? Typically, a Landlab component would represent a natural Earth surface process. Most likely, it's a single process. For example, a soil moisture, which calculates this soil moisture saturation fraction at a given time and space when you're given the inputs of precipitation and PET, or the potential evapotranspiration. Vegetation dynamics model that calculates live and dead biomass over time and space again, given that soil moisture and actual evapotranspiration is given as input. Overland flow, which would plot the hydrographs at a given space and time, or at a given location after a storm. So these are some of the examples, and we are going to cover these during the tutorials after the slideshow. Amanda will be talking about a tutorial, or will be going through a tutorial which would cover overland flow, and I will be going through a tutorial that would cover soil moisture, vegetation, and vegetation dynamics. A component would have a standard interface that would allow it to be coupled with other components. So if you wanted to create a model that's more complicated than a single process, then you can just stack components up and then create a more complicated model. So there are generally two different methods in a component. One is initialize, which is like instantiating the component. And the second one would be update, or an equivalent method called run one step, which would run the process. I've also added some other like figures of, or examples of other available components. There is a shallow landslide probability component, a stochastic storm generator, channel incision component, and you can find more information on this at our documentation page. So I've been talking about grids. By 2D grids, some of the examples are raster model grid, radial model grid, and hex model grid. With Landlab, you can create these grids in the environment with a single line or maybe a couple of lines. On the bottom left, I'm showing you a raster model grid that is created by using the raster model grid module. You can also create Voronoi grids using Landlab gridding engine. So once you create a grid, once you type this command and run it, you have a representation of your surface as a grid, and there are multiple data structures that are created along with it, like nodes, links, and cells. There are 3 more, but I'm going to limit to my discussion to these 3 right now. So a node would be your X and Y location, a data point, and link is a line segment that connects 2 nodes. Cell is the entire surface that is around the closest to the node. We will look at this in detail shortly. Now, I'm looking at a raster model grid again. This has 4 rows and 5 columns. A typical modeling exercise would require you to represent the surface, and next what you would do is to set boundary conditions. So we let you do that. So you can set a node to be open, close, a fixed boundary, or track cell boundary, or a fixed gradient boundary, and each, when you set them, the status at that node would become a 0, 1, or numbers until 4. In Python, everything starts with 0. That's why you see a 0. Be careful with that. So for example, an open boundary node would have 4 as the status of node, and a core node, which is the white circles, will have a status of 0. So by core node, what we mean is that those are the happening nodes. That's where most of the action happens. That's where your components run. But you will have situations where you don't want to work on some of the nodes. That's when you close them, so nothing happens at those nodes, or data flux transfer happens from that node to another node. You can also have a fixed boundary node, which can be used for setting outlets, where data flux goes in and out, but the value stays the same. So I'm showing you core nodes again. So the links can also be set as active and inactive, but it's pretty much decided by the nodes that connect them. For example, a link is always active between 2 core nodes. A link that is connected to a closed node is always closed. A link that is connected from an open boundary to a core node is active. But a link that is connected from an open node to a closed node is inactive. And a link is connecting a tail node to a head node. It has a direction, and the direction is from tail node towards the head node. Let's create a 4x5 grid again. Like we will see, we'll look at the commands that we will need to create a simple 4x5 raster grid. So you import the raster model grid, and then you create the 4x5 grid. You can set the X and Y directional spacing. That will create something like this. We have some useful methods that will help you, or I think we call them methods, to get some information once you create a grid. So you created a 4x5 grid. The number of nodes, it's a no-brainer. You have 20, right? And look at the number of links. By default, when you create a grid, all the perimeter nodes are set to open boundary, I assume. It's either open or closed. So some of the links are not, so there are no links. The core nodes will have 4 links attached to them, but the perimeter nodes will have less than 4 nodes. That's why it's not that straightforward to calculate the number of links, so this will be handy. We can also query number of node rows and columns whenever we want. Same with core nodes and number of cells. Only the core nodes have cells, so they should always be equal. That's something we would like to check. Once you create the grid, you can store data on it. We'll look at that now. We use something called fields. A field is nothing but a NumPy array that is either a scalar or as long as the data structure that you want to attach it to on. For example, when I create rg.addField node elevation z, what I'm doing is I'm creating a nodal field, and I'm calling it elevation, and this is the z is the input value. So what happens is that a NumPy array that is as long as the number of nodes is created and attached to the grid. You can plot this. To plot, we can use one of the Landlab plotting utility called IamShowGrid, which takes in the grid as an input, grid object as an input, and the field name, which is a string. You can look at that on this side bottom, right bottom. Now let's look at the link structures. On the left, what I'm trying to show you is how, so I'm going to talk about node and link structure in this slide. Once you create the grid, the node is, any given node is identified by its ID, and the IDs start from the southwest or the bottom left corner and increase over the east direction or the right direction. They also increase over the north direction or the top direction. So if you create a 4x5 grid, this is how the node IDs would look. So like I said, the status of the node that are interior are set to core nodes by default, and that's why the status of node would return a 0. Now let's look at the link IDs. So the link ID, the number is defined by the tail and the head node. And we can query the links that are attached to a certain node using links at node. We can also look at the directions. So the direction of the link is positive if it's leaving. If this node is the head node of the link, it is negative if it's the tail node of a link. So for 21, the link number 21, 13, node ID 13 is the tail node, and the direction is negative. We can also query the tail and the head nodes of a link. We can attach, like we attached data in the previous slide, we can also access the data using @_node or @_ other data structure if you stored it as a different data structure. So rg@node elevation is a NumPy array, and you are looking at the 13th or 14th position in there because it starts from 0, right? Now we can also change the value of a node because we have access to it. So I changed it to 100, and and we can query it, and we can see that it's 100. So why do we, where can we use this? This can be very helpful when you're doing something where there's a gradient in a field, and you want to calculate the flux divergence, or just to track how much material is leaving a node, or into, or is exiting the node. So here I'm showing you. So let's say we create a field on the node, and you wanted to know the gradient, that is the gradient among the adjacent nodes. Let's call the field, like the scalar field, eta. And when you use the calculate gradient at link, you will be creating an array that is as long as the number of links, and the value is positive when eta is increasing in the link direction. In the sense, if the head node has higher value of eta than the tail node. And if we do that, we can calculate flux divergence using the calculate flux divergence at node command, or the method. Now the dq dx is defined on the nodes because you're calculating at the nodes. So it knows to find all the links that are attached to each node and calculate the net flux in and out of the node. Let's look at it with an example. So on the top left, I have a reference grid with node IDs and link IDs. And let's create a sample quantity, some quantity z on the nodes. So for simplicity's sake, I have set all of the nodes to have that value as 0, but the 7th node has the value as 10. And I calculate d eta dx. So the values on the links are zeros everywhere except the 4 links that I have marked here. So the links that connect 7, the link IDs 11, 15, 10, and 6 have non-zero values. When I calculate dq dx, that gives us the flux divergence on the nodes. What we can see here is that the closed nodes are still 0, even though they are connected to the links that have been affected. But the open nodes have a certain value. That is because the active link has a direction from a value that has been changed to. A fixed boundary node a value can be set there, but it will not be changed on the nodal field that you set the nodes to be open at. So if you wanted to work on a DEM that you have that is external to Landlab, you can always import it into Landlab. We have a handy utility to read in S3 ASCII files. It doesn't have to be a DEM. It can be any other data that is on the surface. So once you read it in, what happens is it creates a grid for you if you don't provide it a grid. So here in the code below, in the code example below, I'm reading the grid that is being created by read_s3_ASCII as mg, and the input file name is some ASCII file, and I'm calling the field that's going to be created on this as elevation. This also returns the elevation values, which can be recorded as a certain variable. In this case, it's z. I can then visualize this information. Now, I also talked about components. We talked enough about the grids. Now, how do we use the components? I apologize for the slide being too dense, but I wanted to show all the steps in a big picture view that would require you to use a component. You would initially create a grid and then import the component from components, landlab.components, and you set all the input fields that the component needs as inputs, and you instantiate the soil moisture component or initialize it. Here you can also read in inputs from a text file or a YAML file and set all the parameters that are not going to change during this process while you're initializing them. Now, this is all component specific, so you should read up the component documentation when you're using a certain component. Now, you can also, if you have missed any of the fields or that it is expecting, you can also give it after you initialize it. Now, you will be running the component or run the component once. In soil moisture component, the method is called update, and some of the components is called run one step. In this component, the current time is being updated, so that's why I'm giving it as an input and also receiving it as an output. And then you can look at the outputs. So we looked at grid, components, and the utilities. And this is how the entire framework sits with respect to each other. To create a model using these components, this is a typical driver setup or the Python script setup. The central part would be generally a grid, and you would attach components to them, and you'll add data or data fields. You can read in input parameters and input data to the environment, and you can write output from it. Now, Amanda is going to walk through a tutorial which is available for you guys so that you can interact with them when she's going through it. And after she's going to talk about the Overland flow tutorial. I'll be talking next about the ecohydrology tutorial.
So I am going to take you through the Overland flow tutorial. Thank you, Sai, for a great presentation. If you go onto HydroShare and search for Landlab_Waterhackweek 2019, or actually I sent it in the Slack as well. So if you go to that collection and open up the Landlab Overland Flow WHW 19, that is the notebook that we're going to be going through. So if you open up the Overland Flow _example IPython notebook, the example that I'm going to go through is actually a comparison of two components, two different ways of solving an equation in Landlab. We actually have a few different components that might have a couple different ways of solving a certain equation, and this is one of the examples. So this is a simple tutorial. I'm only looking at one component at a time. Sai is going to be going through where you actually couple a bunch of components together to create a more complicated model. So for this one, we are looking at the shallow water equations, or the St. Venant equations, known by both names. It's kind of a complicated equation. If you look at it, you have discharge, you have time, you have your location in space, you have the acceleration due to gravity, water depth, bed elevation, Manning's roughness, hydraulic radius, and then your cross-sectional area. So there are 4 different terms in this equation. and each term represents a different process. And so for the first component that we're going to look at, the Kinwave implicit overland flow, it's kind of a mouthful. The approximation that's used ignores, well, it neglects the first three terms in the equation and solves only as if the last term were valid. And then the overland flow component, the second component that we're going to look at, actually only neglects, I believe it's the second term. And it also assumes that the geometry of the channels is rectangular and constant flow width. So the approximation that you use, or that's being used in the overland flow component, is a bit more accurate than what's being used in the Kinwave implicit overland flow component, but it's also a bit more computationally expensive. So this is kind of looking at a comparison of those two, what these two different approximations show and how does that change how we run our model. So we're going to actually be looking at a digital elevation model. The catchment that we're looking at is the Spring Creek DEM in central Colorado. It's 27 square kilometers, and it's a 30-meter resolution. So now we can actually run some code. So if we run the first cell, we're just importing our important Landlab components, we're importing some Landlab utilities, and then we're also importing some other Python packages. Then we can set the initial and run conditions for the first model, the Kinwave implicit overland flow. We're going to say that we're running the model for 6 hours. The storm that we're going to apply to our catchment lasts for 2 hours. Our elapsed time, we have to initialize it at 0. That's when our model is starting. And we are looking at the rainfall intensity of 15 millimeters per hour. And then we have to initialize a couple empty arrays or empty lists to hold some values later on. We set Manning's roughness value, and then we also set a time step. In this case, it's 10 minutes. So if we run that and don't skip over that, we will not have problems when we run other things. Okay, so now we can read in our DEM, the Spring Creek DEM.asc. We're loading it in with the topographic elevation. So we have a grid MG and then elevation values Z. And once we load that in, we want to set a watershed boundary condition such that all of our no data values are recognized as no data values. So in this case, our no data value is negative 9,999. So if we run that, now we can look at setting the where our outlet is for our watershed. We want to make sure that the water is draining to a single point because that's what happens in real life. Well, for the most part. So in this case, we're looking at, we can use Landlab to look at what the lowest point on our DEM is using this first line of code. We're looking at the index at which the core node is lowest. And then once we have the outlet ID, we can set the watershed boundary condition outlet ID such that we have the outlet ID is open and all the other perimeter nodes are going to be closed. And if we run this, we can print out what the outlet ID is. We can print out the elevation of the outlet node, and then we can print the minimum elevation of the core nodes and the maximum elevation of the core nodes. So if we do that, our outlet ID is 55,744, which is a little bit arbitrary, but it's helpful for the model. The elevation of the outlet node is 1876 meters, and the elevation of the minimum core node is slightly higher than the elevation of the outlet node. And this is good. We know that the watershed is going to drain to that outlet node. And then we have our max elevation of 2,611. So now we can actually look at our grid. And if we run this, we get a beautiful digital elevation model. This is what our watershed looks like. So now we've loaded it in, we have our DEM, and we can actually use the component. So Sai talked a little bit about how you have to instantiate your component, and then you also have to run one step or actually run your component. So in order to instantiate the Kinwave implicit overland flow, there are a few different parameters that you need to define or give to your component. So the different parameters that Kinwave implicit overland flow takes are below. So the grid is the model grid, and so we'll be passing it mg. That's required. The runoff rate is optional, but it's in this case we're giving it, and that's the precipitation rate in millimeters per hour. The roughness is Manning's roughness. We are also giving it a value. Changing topo is a flag that indicates whether the topography is changing between the time steps. In this case, it's not, so we don't have to worry about it. And then depth, exp, it's the exponent on the water depth in the velocity equation. And in this case, we're using 5/3 for Manning's. And then the weight that changes the weighting on the depth at the new time step versus the old time step. So basically telling us whether it's implicit or an explicit a way of solving our equation. So in this case, we are going to instantiate our component Kinwave implicit overland flow. We pass it the grid. We pass it an initial runoff rate of 0.0. We pass it the roughness that we defined earlier, and we pass it the depth exponent for Manning's equation. So we run that, and our component is instantiated. So after we actually initialize our component, we can create a driver that runs our component. So I've written in words what the following loop does. So pretty much we're going to look at while the elapsed time of our model is less than or equal to the total model runtime, we're going to loop through 5 different statements. We're going to look at if the elapsed time is less than the storm duration. You run the component using a rainfall intensity of, it says 5 millimeters per hour. It's supposed to be 15, typo. The second, if the elapsed time is greater than the storm duration, then the component is run using a rainfall intensity of 0 because our storm is done. We'll determine the discharge that flows through the outlet node at the current time. We'll update the arrays with values of time and discharge at the outlet for plotting purposes, and then we'll increase the elapsed time by the time step. So if you run this, it actually takes a second to run. And in this case, I've added a print statement to show me that my component is actually run. And so far, it's gone through 10 minutes of the model. So while that's running, I have a pre-run notebook that I'm going to go to so that I can show you what our output is before it finishes. So yeah, it goes through quite a few loops. And so once it's finished, we can plot it. We can plot what the hydrograph looks like at the outlet. So basically, we're looking at the discharge versus time at that outlet that we defined earlier. And this example here, again, the 5 millimeters per hour should be 15. I apologize for the typo. This hydrograph is pretty standard. So like in a physical hydrology class, this is like the example that you would be shown when you're looking at a hydrograph. And then we can also look at the surface water depth at the final time step. So in this case, it's the surface water depth. It's not that high, like at all. I'm not sure how easy it is to see on the big screens. On the little screens, it's a bit easier to see that there's a little bit of water down the center of the catchment. So we can look at the surface water depth at the final time step, but then we can also look at the surface water depth at different time slices because it's a little bit more illuminating. So pretty much we can rerun the driver. Like the driver is very similar to what we had before, except this time we're plotting for each time slice. So this is still running. So I'm going to continue with the pre-run version. So if we reset our elapsed time to 0, we define different time slices for the water depth plots. In this case, we're going to look at a water depth plot for each of the hours that the model is being run. You can convert the time from hours to seconds so that the model knows what we're doing. So in this case, we basically just have an extra for loop. So we're looping through the time in each of the t seconds. We run our elapsed time while the elapsed time is less than the model run time. We run our component, run one step, pass the time step, pass the current time, which is the elapsed time, and pass the runoff rate. And if it's less than the storm duration, we're passing it the runoff rate. If it's anything else, we're passing a runoff rate of 0 because our storm's done. And then we have figures for each of the different time slices. So if we look at this, now we have a bit more information about where the water is going as the storm progresses. So at 1 hour, we have this. We have 2 hours, 3 hours. That's when 2 hours is, let's look at where the peak is. The peak is just before 2 hours. So this is this surface water depth plot here. 3 hours, the water is draining out. 4 hours, 5 hours, and then the final 6th hour, which is what we had plotted before. So that's what the kinematic wave approximation looks like. The typical hydrograph that you would see, generally it's a kinematic wave approximation because it's simple and it works for a lot of different situations. It's a pretty good approximation, all things considered, and it's less computationally expensive than other approximations. But now that we've actually used that approximation, we can try the Overland flow, which is the approximation that I believe it's called the diffusive wave approximation. So if we reinstantiate our elapsed time, make it 0, and then zero out our arrays from earlier, our lists from earlier, we can reload our DEM and plot it and make sure that we don't have anything that's crazy. It looks the same, so now we know that we can go on and actually work with the Overland flow component. So before, I talked a little bit about what you pass for the kinematic wave component. In this case, we'll look at what the Overland flow component is passed, and it's slightly different. So you pass it the grid, which is typical for pretty much every single component. You pass it or there's an optional thing to pass a thickness of an initial thin layer of water, and this is just to prevent any divide by zero errors. Alpha is a time step coefficient. It's described in these papers listed here. And in this component, actually, the code author, Jordan Adams, she decided to use an adaptive time step. So this alpha is part of that piece, and the adaptive time step is really there to help ease the load of the computational intensity for this specific approximation. So that's what alpha is for. Manning's n, similar as before, we pass the acceleration due to gravity. Theta, it's a weighting factor. The rainfall intensity is just the rainfall intensity. And then steep slopes, this is to ensure that the water isn't draining too fast for the time step. So that's just a flag. In this case, we're going to be setting that to true. So yeah, for this tutorial, we're defining the grid, the Manning's n, and steep slopes. And we also define the rainfall intensity, but that occurs during the component driver. So the driver is very similar to what we did before, but we have a little bit extra where we actually calculate the adaptive time step for the current time. And then we go through the same steps. If the elapsed time is less than the storm duration, we pass it the rainfall intensity. If it's greater than that, then we go through and pass it a rainfall intensity of 0. We have to map the surface water discharge onto the nodes because in this specific component, she actually is calculating the water depth on the links. And so we map it to the nodes. And then we can update the arrays with the values of the time and discharge, and then increase the elapsed time by the adaptive time step. And again, we could run it, but it takes a bit. And so we print out the elapsed time just to make sure that it's not leaving us hanging. And it printed out a lot because I forgot that the adaptive time step changes the time step each time. So I got a lot of different time slices. So I'm just going to scroll past all of that. And now we can actually look at the outlet hydrograph and see how it differs from what we saw before. And in this case, it's not quite as smooth as what we saw before. It's probably a bit more realistic. The peak comes a little bit later. It's closer to 2.5 hours, 3 hours than it was to 2 hours. It seems like there's like a little nick, like there are a couple little nicks here. And I'm not entirely sure if that is naturally occurring or if it's a numerical, just a weird numerical issue. But we can look at the surface water depth at t equals 6 hours again. And here it's not exactly illuminating. So we can look at all the different time slices. So we have 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, and 6 hours. And these water depth plots actually look very similar to what we saw with the kinematic wave. And so that is how you go through and run these two different overland flow components. You can see a bit of a comparison, see how they differ. If you wanted to save your time and discharge arrays to a file, you can use an np.savetext, which is a NumPy function. And if you wanted to save any of your plots, you can do plt.savefig. So this was a very basic component tutorial. If you wanted to look at these components in a bit more detail and look at their use cases in more detail, I've linked to another tutorial. Well, in this case, I can't click on it. But that, or maybe I can. Haha. It's a HydroShare resource from Christina Bandaragoda. So that is all I have for the Overland flow. And now I'm going to turn it over to Sai so that he can go through the eco-hydrology example.
So if you look at the HydroShare resource, which the collection, I have linked the resource called Landlab Eco-Hydrology Tutorial to it. If you open that, you will see the resource, and you can open the resource using Quasi Jupyter Hub on the top right. Once you do that, you will see a IPython notebook in it called ecohydrologic_mapping.ipynb, and click on that. That should open a notebook something like this. And thanks, Amanda, for going through the Overland flow tutorial in detail. And I hope you guys are now have a good idea about what a component is, how a grid is connected to a component, how can you use a different component if you want to change the component, and how you instantiate a component, and how you run the process. In this tutorial, I'm going to go through the eco-hydrological model, which we will build step by step. And we'll use 4 components that are radiation, potential evapotranspiration, soil moisture, and vegetation. So what we are going to do is plant grass on a landscape and check how it's doing, or it would do, at 2 different time steps or 2 different days. And the days that we would select would be, one would be the summer solstice, that's middle of the year, and the other one would be end of the year during the winter solstice. So let's get going. I have also provided a sample DEM, and this DEM is from a catchment in central New Mexico. The latitude is 34 north. It's situated in Savieta LTER. Let's import the required packages first. Okay, there you go. So what I'm importing are all the components that we're going to use. I will import soil moisture and vegetation dynamics later. For now, let's import radiation and potential evapotranspiration. I need to visualize the grids and the data stored on it, so I'm also going to import the utility read_esri_ascii. Sorry, that's for the input of the DEM, reading in the DEM. And I will use imshow_grid, the Landlab plotting utility for plotting. And now I'm reading in the watershed, and I'm showing the watershed here. So what I did was I collected the elevation that was from the DEM and created a nodal field, a field on the nodes called topographic__elevation. The names of the fields are standardized a little, or they are standardized internally for Landlab, so that we convey most of the information that is associated with this field. So we apologize if they sound too long or are too long. So there is an elevation gradient from 1700 to 1660, but there is also an aspect in here, in the sense that this is a catchment that shows that is a good example to study the influence of slope and aspect on the vegetation organization. So there are distinct ecotones. And to get an understanding of that, I'm going to plot aspect. So if you look at the DEM, the top face or the top direction is the north. And you can see that, so I tried to plot only hot and cold colors for north and south facing, but unfortunately the NumPy changed something, so I have to look at their information to change that. So for now, the hot and cold colors, the red and blue, both represent the north-facing slopes. We have two distinct ones here. And the milder colors are greenish, yellowish colors are south-facing slopes. Let's remember that. We will see, I think we will see something cool. Now let's instantiate radiation and potential evapotranspiration components. If you want to read more information on these components, please click the links. And what I'm going to do is I'm going to use the grid as the input for the radiation component. And I'm going to set the latitude to be 34 degrees. This component is going to give us an output of the ratio of radiation input to a sloped surface with respect to a flat surface. And we also will instantiate the potential evapotranspiration component. The potential evapotranspiration component can actually function with different methods. It can also use a Penman-Monteith method. In this case, we're going to use Priestley-Taylor, and we're going to set latitude to 34, elevation of measurements to 2 meters. There are other optional inputs which we have set them by default so that you don't have to worry about it here. And like I said, we're going to run this model over the tutorial at 2 different time steps. The first time step is summer solstice, and the current time for that is 0.466. It's in years, and the corresponding date is June 20. We will use a T minimum of 14 degrees, T max of 32 degrees, and T average of 23 degrees as input. So I have set the current time to 0.466. I have run the radiation component now with the time. So I have the ratios for each cell in the watershed that gives us the value of the ratio of shortwave or the total input radiation when compared to a flat surface. And then we can run the PET component. So PET component is going to calculate the potential evapotranspiration at a point and then distribute it using the ratio that we calculated from the radiation component. So that's all automatic. Once you created that field called, let's look at the name of the field. It's called radiation __ ratio to flat surface. Now, when I ran radiation update, it updated the field that was set on the grid called watershed, and PET component read it from the grid. So we don't have to pass along NumPy arrays among the components. And now let's look at what outputs the potential evapotranspiration component is giving. So we have surface potential evapotranspiration rate that is being calculated, and net shortwave flux. Let's look at net shortwave flux first. Even though the range is probably not that significant, but we can actually observe the aspect influence here. The south-facing slopes have slightly higher radiation input with respect to the north-facing slopes. And let's see if we observe the same trend in potential evapotranspiration rate. Yes, we do. We should. And that's because of the ratio to the flat surface, right? Now let's instantiate soil moisture and vegetation dynamics components. And we will use a vegetation type of grass. You could use either a tree, a shrub, or a grass. We will use grass now. The assumption here is that each cell can have only one plant functional type on it. So if you set the vegetation type to be 0 on a cell, then only grass is there at a given time. And we can also set vegetation cover. So what that means is that the cell is covered only 50% with the vegetation. We can set initial soil moisture saturation, and we can also set a rainfall value or the storm value, the storm depth. In this case, we'll use 50 mm. And we'll use an interstorm time as 15 days, which means that there will be no storm until 15 days after this one. The soil moisture component simulates the soil drying process after a storm. So it takes into consideration how much water has come in to the system and how much has evaporated and what is the soil moisture saturation rate at that time, at the end of the storm. For vegetation component, we'll use the initial live biomass as 30 grams dry matter or area, and the same value for a dead biomass. So every component needs an input fields, a set of input fields. So we know that we have to give in rainfall daily depth, soil moisture initial saturation fraction, surface potential evapotranspiration rate, which we already calculated from by running the PET component. And we do have to give an input of cover fraction, live leaf area index, and plant functional type. And let's see what we'll get out of the component. We will get the root zone leakage to the groundwater, and saturation fraction, or the water content, or the volumetric water content, and the actual evapotranspiration that occurred there, runoff, and water stress. Water stress will denote how much stress the vegetation that's sitting there would experience due to the closing of stomata based on the current soil moisture conditions. We can also query the units of these fields. So we know that we have to give input of the plant functional type. So we can set it to the plant functional type we decided. Since this is a cellular field, a field on the cells, I need to give it an input of a numpy array that's as long as the number of cells. To do that, I use the numpy.full command and set the shape to be watershed.number of cells, and give this is the input value that's going to be populated. So it's going to create a numpy array that's as long as number of cells with the value of vegetation underscore type. And I'm also setting the the data type as int. And I'm going to instantiate soil moisture component here. And we need to also assign initial soil moisture saturation fraction, rainfall daily depth, and cover fraction. So we do the same thing. We give in numpy arrays with the same value. And let's look at the initial values that we set in. So it's the same, it's a constant value that we gave in for inputs. And now I'm going to run the soil moisture component. So I'm going to update it. It takes in the current time and also updates the current time and spits it out. It is expecting, the update method is expecting the interstorm duration in hours. What we set was in days earlier, so I'm going to multiply that with 24. And let's look at the soil moisture saturation fraction now. Not much of a range, but we can see the topographic influence on it mildly. And let's run vegetation component now. Let's look at the watershed. Water stress. Again, the south-facing slopes experience slightly higher. I'm not sure if that's significant enough, but the map shows a topographic influence on it. And to run the vegetation component, let's provide it with all the input fields. Okay, one of the input field is potential evapotranspiration 30-day mean, which we use to decide whether it's a growing season or a dormant season. So for simplicity's sake, we will use the same data as the potential evapotranspiration rate for it. And let's instantiate the vegetation component and update it. So run one step. And we can look at the live biomass and the live leaf area index. Let's repeat it. We can also look at the data if we want to, instead of like mapping it. We're looking at surface evapotranspiration and root zone leakage. Now, once you're done, you can save this as a NumPy file or save it to a different, bigger NumPy file or use it for your analysis. Now that we have gone through this step, we have looked at the summer solstice. So let's go and change that to the winter solstice and run this again. To run that again, I'm going to use the current time as 0.997 and Tmin as -5 degrees. It's a cold day. And the maximum temperature as 11 degrees, the average being 3. And I want to run all of the cells again, just to make our lives easier. Let's use the Jupyter hubs, run all below. Okay, let's look at the results. I'm sorry that I'm scrolling. Just give me a second and we can look at the results now. Okay. Now we can see a better aspect influence in here. The range is way higher for the net shortwave flux. Let us compare it to what we saw earlier. So give me a second. I have included the expanded notebooks to the actual collection. If you wanted to look at them, if you don't want to run them and just look at the outputs, you can do, and you can open them like I'm opening it. So like I said, during the winter solstice, we can see a distinct aspect influence on the shortwave and potential evapotranspiration rate. And let's look at how soil moisture is. This is the initial soil moisture. Now you can also see a clear aspect influence here. The south-facing slopes have lower soil moisture compared to the north-facing slopes. Since there is less evapotranspirative flux, you have more of moisture left. It seems there is no water stress, so plants are happy. And let's look at live biomass and dead biomass. We don't see any differences in values. Why is that? The previous case, the aspect influence due to the potential evapotranspiration rate was evident in the live biomass generation, right? So I'm showing you the previous run for summer solstice. We have some differences in the watershed, but during the winter solstice, there's no difference. It's because it's the dormant season, there is no influence of evapotranspiration rate on the biomass of grass. So this is how you stack up different components if you want to and create more complicated models. You can run these models again if you want to change the parameters, change the plant functional type if you want to. If you change the plant functional type, make sure that you also change the default values if you have to, and try again. If you face any issues with either of the tutorials, please reach out to us, to one of us, and we'll be able to help. Before I end, I would like to ask you guys to check our documentation page. I spend a lot of time here, and we have all useful tabs, but two of them stand out for me: user guide and reference manual. If you're starting working with Landlab, I think user guide is a good place to start, or you can also look at the reference manual. This is more like an API where you can get a lot of details really quick. So we were going through some of the useful methods. So there are many others that you can use when you're modeling with Landlab. Just showing some that are used for the raster model grid. You can also read up on the different components and try our tutorials. If you guys have any issues with Landlab, please create an issue on our GitHub page. We are open to public on GitHub. And if you create an issue, one of us will definitely answer within a couple of days, max. It is a lot faster generally. Any questions now?